All right. This is in the open textbook. This is section 3.9. So this video at derivative of power x. Now, if you're in like calculus class, I may have told you before. We have already learned this is a function whose derivative is itself. That makes it special. It's nearly unique in that way. The only other functions that that satisfy this would be like constant multiples of this function. Anyway, so it's pretty much unique in this rule. But today I want to actually prove that this is the case. Right? We're gonna look at an explanation of why this function is its own derivative. So before we really dive into that, we need to discuss an important limit. There is a limit we're going to be using for this proof, which is this one. The limit as x approaches 0 of 1 plus x to the power 1 over x. And that limit turns out to equal about, I should put approximately here, 2.718281828459045, and then no. You might recognize this number. This is the number e, Euler's number. It's the base of the function e to the x. So to convince ourselves of this limit, we're not going to solve it analytically, but rather we're going to solve it. We're just going to look at it numerically. So what I want to do, what I've got is I've typed in the function 1 plus x to the power 1 over x. And I want to go ahead and look at what happens when x equals like 0.01, 2.704 something. Let's make this whole page a bit bigger. There we go. We're looking here. If I get a little bit closer, 0.001, 0.0001, you can see I'm getting 2.7181 for, okay, so I'm getting closer, 2.718281. Okay, we're pretty close. Negative 0.00001, on the other hand, gives us something likewise close. Like these round about the same value, and the value we're seeing here is e, 2.718281828, so on, so on. That's what we're seeing here. Okay, being rounded, but that's the number we're approaching. So I know that's not proof by any means, but we're going to take this particular limit for granted, and we're going to lean on this fact that this limit equals e. We're going to lean on that for our exploration of the derivative to come. Now, this has an interesting sort of result, because that means that when x is near 0, you can write 1 plus x to the power 1 over x. That's approximately equal to e. And if you take both sides of this equation and raise it to the power x, you get an interesting result. And we need the parentheses to write, yes. An interesting result is because the 1 over x and the x multiply together, right? When you take a power, like an exponential expression, and raise it to another power, you can multiply the powers together. That's one of our rules for working with exponents, right? So 1 over x times x is going to equal 1, right? Those cancel each other out. That equals 1. So the result is 1 plus x is approximately the same as e to the power x when x is near 0. I can actually write that over here. Now we're going to use a version of that doesn't involve x. Instead of x, our version is going to involve the delta x, or h, as we call it, when you use a limit, when you use a different quotient. Okay, so that is the approximation we're going to use. It's valid when h is near 0. And the nature of a limit is such that this approximation is like gets more and more accurate the closer you get to 0. So if you're taking a limit as h is approaching 0, which we will be when we try to evaluate the derivative in just a minute, then you can get arbitrarily accurate, which means like the closer you get to 0, the closer you get to 0, the more and more accurate this gets to an arbitrary degree of precision. It means you can make it as precise as you want to to any number of decimal places, precision-wise, by just selecting an h, which is like sufficiently close to 0, like get closer and closer to 0 and be able to get as precise as you desire. Anyway, so let's go ahead and with that setup, let's go ahead and look at the derivative of this function using the definition. All right. Let me call this a bit. Ooh, all right. A little bit of housekeeping. I'm just gonna move that up, make it all a bit smaller, perhaps. All right, gotta have some space. So we're gonna look at the derivative of e to the x, and the definition of this is a limit as h approaches 0. We're gonna do e to the power x plus h, all of that inside the function, right? And minus e to the power x, and then all over h. All right, get ready, because we're going to use some properties of exponents here. Just stuff you would have learned in an algebra class a pretty long time ago. Okay, so nothing fancy, just a review of some algebra. When you have an exponential expression with two powers that are added together, remember that you can rewrite that as like a product of the two exponential expressions. You multiply the two exponential expressions together with the same base. You can combine them by adding the powers. But we're just doing the reverse of that and separating them apart. Okay, so we have that minus e to the x, and then all over h. Okay, great. So then what we can do is factor out e to the x, right? We'll see here we have an e to the x right here and right here. So we're going to factor it out. That whole e to the x is multiplied by e to the power h minus 1 all over h. Okay. Now, here's something that we've talked about before when we were looking at the derivative of the sine function in a previous video. I mentioned how since this limit is with respect to the h variable, that's what we're paying attention to, like what happens as h equals 0. Any portion of that, any like factor within there that doesn't rely on h, it doesn't like depend on the value of h, it basically can be treated as if it is constant with respect to this limit. So this e to the power x, that is a factor that doesn't rely on h, right? It's just a function of x, and x is some other independent variable. So we can treat it as if it is a constant, pull it out using the constant multiple rule for limits. All right, so we have e to the power x on the outside, and then times the limit as h goes to 0 of just this, e to the h minus 1 all over h. Okay, now is the moment when we get to use our special tool that we've set up specifically for this job. We're going to take that, nice big bold star here. We're going to take this approximation, the idea that e to the power h is approximately the same as 1 plus h when we're close to 0, which is exactly where we want to be, right? Approaching 0. And we're going to go ahead and substitute it in there. E to the h is going to be substituted with 1 plus h. So what we have is this will equal, not only approximately, I don't even have to write approximately here. I can actually write equal because of the fact that we're dealing with a limit, which means h is arbitrarily close to 0, okay? But this precision is arbitrarily good, which means that when you actually go all the way to 0, which doesn't really happen, but you kind of imagine it happens, it's exactly the same thing, right? They're exactly equal to this. I don't even have to write approximately here. Oops, sorry, I got worked up. I got kind of excited there for a minute because this is a really neat concept. One of the beautiful things about Linux is you can get precision out of approximations. I find kind of, just mind blowing way. All right. Rein me in here. All right, so what we have now is you've got this e to the x, which is still there, times the limit as h goes to 0 of, and then I'm going to replace the e to the h by the 1 plus h. And then I have minus 1 and all over h. And now we see something really nice happening, which is 1 minus 1 cancels out. And we have h divided by h, which equals 1. So this is the e to the x times the limit of 1. And that's 1, right? So this is just e to the x times 1, which is just e to the power x. And what have we shown? We have proven derivative of e to the x is itself. And that is what we set out. Now I hope you could see, I know this is based on a limit, which we can on space, but the limit, you could graph the function and it's pretty clearly approaching e right over here. So, I think you should be pretty well convinced. But at least we have now this sort of like rigorous foundation on which to build the rest of our derivatives. And so we're going to next see if we can figure out derivatives of other exponential functions as well as logarithmic functions. And we don't have to use the limit of the difference quotient for the next few videos because we can lean on this fact in combination with things like the chain rule and implicit differentiation and so on. So that's what we're going to do next.